So today we are going to discuss October 2025 Unit 3 Edexcel paper. So starting from question number 1, they are saying two organic liquids. S and T are isomers and have the molecular formula C3H8O. The table shows some chemical test carried out on S and T. So first of all, it's C3H8O. It has only one oxygen. So we have to think one oxygen is in aldehyde, one oxygen is in alcohol as well, one oxygen is in ketone as well. It can't be carboxylic acid, it can't be ester. In ester we have two oxygen atoms, in carboxylic acid we have two oxygen atoms. So it may be alcohol, it may be a carbonyl compound. So I have tried after drawing the structures of uh, carbonyl as well and alcohol as well. So this formula is fitted on alcohol completely. So I have decided that this is an alcohol. Right now, I don't know. It's a primary alcohol. It's a secondary alcohol. I would see after looking at this table, right? Okay. So they are saying heating isomer with potassium dichromate. That's an oxidizing agent. We all know it's a very common oxidizing agent. Okay. So they are saying positive. We know primary alcohol can also be oxidized. Secondary alcohol can also be oxidized. So they are saying this is positive. So it may be primary alcohol, it may be secondary alcohol, but they are saying the positive test. So I have to write down the observation. It would be from orange to green. It would be from orange to green, okay? Because initially the color of potassium dichromate is orange and afterwards it's going to be green. And also they are saying about T, okay? They're saying about T. S and T, they are isomers of each other. So the same as the observation in S means the T is also giving the positive test. Means the T is also giving the positive test. It means that the color change would be the same, okay? And then we have to say this, method of heating. They are distilling, they're refluxing. So the thing is, that in distillation process, 1 degree alcohol is converted into an aldehyde. In a refluxing process, 1 degree alcohol is converted into carboxylic acid. That's the concept. Okay. Now, failing solution. We know that this is the test to check the presence of aldehyde only. So it's giving you the positive test. Okay, so observation is brick red precipitate is formed. Okay, no visible change. It means that this is going to be ketone, right? It's mean that this is going to be ketone. That's why the failing solution is not giving the positive test with the T, because the result is negative. The result is positive. Why? This is an aldehyde. So I can opt a conclusion from that. S was oxidized. It means that it was a primary alcohol. It gave us aldehyde. It was a secondary alcohol. After oxidation, it gave us a ketone. That's why the failing solution is giving the positive test with an aldehyde. It's not giving the positive test with a ketone. Then addition of sodium carbonate solution. Of course, carbonate is a base. It can only react with an acid. So no visible change, no visible change, negative, negative. It means that there is no carboxylic acid. This is confirmed. This is confirmed that it's not a carboxylic acid. It was an aldehyde and it was a ketone. Okay. The isomers S and T have the same functional group. Identify the functional group. Alcohol. They both are alcohol. They both are alcohol. They both were oxidized. That's another thing. The first one was primary alcohol. The second one was secondary alcohol, but they were alcohol. They was oxidized. Okay, because ketone cannot be oxidized. Aldehyde can be oxidized, but the thing is the formula is not fitting on an aldehyde. I drew it, but it has six hydrogens, but in the formula it has 8. So finally it's wrong and it's right. Okay, it's a further confirmation. Draw the skeletal formula. So of course I know isomer S was primary alcohol. So this is a primary alcohol. Having four carbon atoms? It has four or three? Three. Okay. So one, two, three, and it's a secondary alcohol. So one, two, three. That's it. Simple. And they are saying two organic compounds, U and V, are group two halides. It may be calcium chloride, it may be magnesium bromide, group 2 halide. Halide bole to like group 7, right? In a flame test, compound U produces a yellow, red, or brick red color. It's mean that that's going to be a calcium. Okay, that's the color of the calcium. And compound V produces a pale green color. That's a barium. So give the formula of each of the group 2 cation present in compound U and V. So it's a quite clear. It's calcium and it's a barium. That's it. Suggest a chemical test and expected result to confirm the group 2 cation present in a solution of compound V. Like I have to test barium. So I would be adding sulfuric acid in a compound V. It would give us a white PPT of barium sulfate. It would give us a white PPT of barium sulfate. Remember, whenever you are going to check the presence of barium, so we have to add sulfuric acid. After adding sulfuric acid, it would give us the white PPT of barium sulfate, and that's the barium. That's a barium, remember. Okay. So, uh, to test for the halide ion, a few drops of dilute nitric acid and aqueous silver nitrate are added to separate solutions of U and V. A solution of U forms a yellow, means iodide. A solution of V forms a cream, means bromide. Give the formula of the halide ion present in U and V. Of course, for U, it's iodide. So I wrote it. In the solution V, it was bromide. So they are saying ion. So I wrote I minus. They are saying formula of the precipitate. That's the precipitate. So I wrote AgBr. Someone who would write Br minus, he would not be getting the correct answer. He would not be getting the mark basically. Okay. So they are saying ion. So I wrote ion. They are saying precipitate, like the compound to which, due to which you are getting the precipitate. So I wrote AgBr. Okay. So give a chemical test and its expected result to confirm the identity of the halide ion present in compound V. So, you must know these two tests for the halide ion. If you remember, we used to add silver nitrate and nitric acid. And after getting the precipitates, like the white PPT for the chloride, the cream PPT for the bromide, the yellow PPT for the iodide, and then we used to add ammonia, remember. So I know that in a compound V I had bromide. So how can I confirm it? I'm going to add dilute ammonia. So then the cream PPT is insoluble in the presence of dilute ammonia. And then we have to add concentrated ammonia. In the presence of concentrated ammonia, the cream PPT gets soluble. You have to memorize this. You have to memorize this. Okay. The first one, what if I'm going to add silver nitrate? So, okay, I got like, there may be chloride, there may be bromide, there may be iodide. Let's say if I have a bromide, so how can how can I confirm this? It's a CT test, confirmatory test. So then I have to add ammonia. Okay. Simple. For the iodide, there is something else. For the chloride, there is something else. You have to memorize this, right? I'm going to paste a link on which you can see all the possible tests regarding the halide ions. Now, washing soda is hydrated sodium carbonate. Okay, the value of N can be determined by titration. Okay, the titration was carried out using the following procedure. They have weighed 4.29 gram of sodium carbonate in a beaker. Like I have taken a beaker, in which I have sodium carbonate, that is 4.29 grams of sodium carbonate, then was dissolved in 50 cm ionized water, DI water. That's a pure water, 50 cm cube water. Okay, all of the solution was transferred to 250 centimeter cube volumetric flask. So I have transferred this solution. I have transferred this solution into a volumetric flask, into a volumetric 50 centimeter cube. I have transferred all the solution to this flask, right? Okay. So the beaker was rinsed with deionized water, and then these washings were added to the volumetric flask to make sure all the particles are transferred from this beaker to the conic to this volumetric flask. Just to make sure, okay? The volumetric flask was made up to the mark, like this is the mark. With DI water, the flask was stopped and inverted several times so that the sample can be mixed in a proper manner, because we are going to make a solution, right? So a burette, pipette, and conical flask were all rinsed with DI water. Okay, 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 okay. The burette was rinsed and then filled with this much like concentration hydrochloric acid solution. The pipette was rinsed with the carbonate solution and then used to transfer this much solution to the conical flask. Then methyl orange were added to a flask. The sodium carbonate solution was titrated with the hydrochloric acid. This step was repeated until concordant, like the same similar readings were obtained. Give a reason why the volumetric flask was inverted, of course, to make sure all of the washing soda is soluble in water and forms a uniform mixture. Okay. Like the thing is why you are going to shake it, why you are going to mix it, why you are going to swirling the flask for several times. Of course, to make sure, because when you are going to dissolve sugar in water, so you have to like stir it. You have to shake it. Why? To make sure all of the sugar should be dissolved in water and you can get a uniform homogeneous solution. In step 5, the burette, pipette, and conical flask were all rinsed with DI water. In step 6, only the burette and pipette were rinsed again with their appropriate solutions. Give a reason why it was not necessary to rinse the conical flask again. That's the conical flask, right? Whenever we do titration, that's the conical flask and that's the burette. Okay. So they are saying why it was not necessary to rinse the conical flask. Yep. So the titration result will be unaffected. Why? Why? As the dilution does not change the number of moles of the solution present in a conical. Remember, whenever we are going to do a titration, so it's the reaction between the number of moles of acid and the number of moles of alkali. Okay, so if you are going to rinse it, so means that the reaction is between the moles of acid and a moles of an alkali. So it would not be affected. So that's the reason it's not necessary to rinse the flask again. Then they are saying state the color change at the end point of the titration in step 7. We have added methyl orange. We must know the color of methyl orange in acid. We must know the color of methyl orange in a base. So it's yellow in base and orange in acid. Sir, how did you know? Why not? It's from orange to yellow. Why it's from yellow to orange? It's a very tricky question. To answer this question, you need to know which substance is present in a burette and which substance is present in a conical flask. Because we add indicator in a conical flask, not in a burette. So what is present in a conical flask? Of course, you can see I have added sodium carbonate in this volumetric flask, and they are saying pipette, pipette was rinsed with the sodium carbonate solution and then used to transfer 25 cm cube of the solution to the conical flask. The thing is, I have taken 25 centimeter cube to the to the conical flask. So I have sodium carbonate in a conical flask, and we know that's a base. I have added few drops of methyl orange. That's why I can see yellow in color. After the titration, it would turn into orange. That's it. Simple. Okay, that's the results. The following results were obtained in a titration. So they have given, I have subtracted these two to get this, subtracted these two to get this, subtracted these two to get this. Then they are saying, then they are saying, complete the table and calculate the mean titer using all concordant values, the similar values. So what I did, I have to check the difference. The difference between these two, the difference between these two, the difference between these two. So they are quite closer to each other. 24, the difference between these two is zero point 0.5. That's okay. The difference between these two is zero point 0.1. So 1, 2, 3. They are concordant readings. So just what I did, sum of all the values divided by the total number, you would be getting the mean titer. Then complete the equation for the reaction. It's a very easy question. It's a very easy equation. It's from IGCSE. Of course, it's not new for you. Sodium carbonate is reacting with HCl and it's going to form salt, carbon dioxide and water. Then I have balanced it. That's it, simple. State symbols are not required. Calculate the value of N in the washing soda using your answers from B part 1, B part 2. You must show your working. So now I have calculated the moles of HCl. How? They have given the concentration of HCl, that's 0.125. You can see this. Multiplied by the volume that I got. It's 24.00 centimeter cube. And then I got the moles of HCl. I know the equation. I know the mole ratio between sodium carbonate and HCl. That's 1:2. So if I have 1 mole of sodium carbonate according to equation and 2 moles of HCl, and I have 0.000300 moles of HCl, what would be the number of moles of sodium carbonate? In short, I'm going to take a mole ratio to know the moles of sodium carbonate. That's the mole of sodium carbonate. Now I have to take the mass. I have to calculate the mass. Mass is equal to Mr. Moles. MR of sodium carbonate is 106. So I got the mass of sodium carbonate, that's going to be 1.59 grams. 1.59 grams. That's the mass of Na2CO3. Now I'm going to calculate the mass of water. How? I'm going to subtract the mass of sodium carbonate from hydrated sodium carbonate. The total mass for this they have given in the question is 4.29 and the mass of this is 1.59. So let's subtract it from the formula. Of course, I would be getting NH2O, isn't it? I got NH2O, that's 2.70. I have to calculate N. N is the moles. Water is being multiplying over there. It would be divided. The molecular mass of water is 18. So it's going to be 0.15 mole of water. This is the mole of sodium carbonate. This is the mole of water. This is the mole of sodium carbonate. This is the mole of water. Now, if you remember when you used to calculate the empirical formula, you know the steps. Firstly, we used to calculate the moles, then we used to calculate the simple moles by dividing with the smallest number. Okay, I'm going to do the same. I know this is the smallest number. I'm going to divide it with the both. So I would be getting 1 and 10. So the value of n is 10. That's it. Simple. Then in question number 4, they are saying a student was provided with a mixture of anhydrous potassium carbonate. Okay, anhydrous, right? There is no water. An anhydrous potassium hydrogen carbonate and carried out an experiment to determine the percentage composition of this mixture when an anhydrous potassium hydrogen carbonate is heated. It is decomposed, producing potassium carbonate, carbon dioxide, and steam. Anhydrous potassium carbonate is unaffected by heating in this experiment, as this is already anhydrous. There is no water. Write a balanced equation. Okay, it's going to be decomposed, and they have told us it's going to give you potassium carbonate. carbon dioxide, and steam, that is water. Then we have to write state symbols. Then I would be getting solid, solid, gas, gas. So this is of 2 marks. And then they are saying state why the crucible has a lid and it is important that it is loose fitting. Yeah, it's important to have a loose fitting. Why? So that during heating, mixture retains and crucible and gases can escape easily. If this is tightly, you can say, like tightly fitted, the lid is tightly fitted. What does it mean? A gas cannot escape from this crucible, which is quite dangerous. The pressure would build up and it can explode. So, but there should be a lid. If you're thinking, sir, you are supposed to remove the lid. No, you are going to heat it. The substance is being decomposed. Might be possible some of the particles would escape from this crucible and they fall to the ground. Of course, there would be a loss in mass. So there would be some sort of error in your calculation. Okay. So give the reason why this mixture was heated to constant mass just to make sure all CO2 and water should be removed from the crucible. Because let's suppose I have 100% hydrated compound. I'm going to heat it. The water molecule is going to remove from the compound, and then you are going to take the mass. Initially, the mass was 10 grams. After heating for 1 minute, I got the mass 8 grams. So there is a loss of 2 grams in the form of steam, water. Now I'm going to heat it, then I'm going to take a mass. Now I'm going to heat it, then I'm going to take a reading. When after heating, I would be getting the constant readings. It means that it is confirmed that all the compound is decomposed. Now it's not getting decomposed. The reaction has been stopped. Nothing is removed from that compound. So just to make sure, why the mixture was heated to constant mass, just to make sure all the gases like CO2 and water should be removed from the crucible, and that's it. Okay. Then 12 gram of a mixture of anhydrous potassium hydrogen carbonate and anhydrous potassium carbonate was weighed by the student after heating to constant mass. 8.90 gram of solid remain. Calculate the percentage by mass of anhydrous potassium. This is K2CO3. Potassium carbonate is K2CO3. That's the potassium carbonate, right? Okay. So if you remember when we used to calculate the percentage yield, what was the concept? What was the concept? The concept, the formula that in the end we are going to apply the mass of K2CO3 divided by the total mass multiplied by 100. But where is the mass of K2CO3? I have to find it out. I have to find it out. Then I'm going to put it in the formula. Then I would be getting the percentage yield of potassium carbonate. So, so this all working is just to calculate the mass of potassium carbonate. Got it, right? So we have to apply this formula and we would be getting the percentage yield. That's it. So number one thing is that this is the total mass. So mass of lost substances, total minus the remaining, total minus the remaining. So means that it would be the mass of CO2 and water. Of course, these are the lost substances. If you have gone through this equation, this is the solid, it would remain, and these are two gases. So the gas will escape. So the gas will escape into the atmosphere. So the gas will escape into the atmosphere, right? And the solid would remain. And the solid would remain. Okay. When the solid would remain, so that would be your remaining substance. And this would be your like the lost substances. And then what I did, the total mass minus the remaining one. So this is the mass of lost substances. That is CO2 and water. Okay. Now, mass of mole of lost substances. Of course, mass over MR. Of course, mass over MR. Mass is 3.1. MR of water is 18. MR of carbon dioxide is 44. I'm going to sum it up. I would be getting the moles of the lost substances. Okay. Then I have to find out the moles of KHCO3, right? I have to find out the moles of KHCO3, right? That is according to the equation KHCO3 and the lost substances. The mole ratio is 2 is to 2, like 1 and 1, like 1 and 1. You can see the lost substances. It's going to be 2 is to 1. 2 is to 1. So I got the moles of lost substances, that is zero point 0.1 mole of KHCO3. Okay, KHCO3, right? Okay. So then I have to find out the mass of KHCO3. Mass is equal to Mr. Moles. MR of KHCO3 is 100.1. MR of KHCO3 is 100.1. So it's gonna be mass of KHCO3, that is 10.0100 grams. Okay. And then I have to find out the mass of K2CO3. I have to find out the mass of K2CO3. So how can I find out the mass of K2CO3? That was the total mass of anhydrous potassium bicarbonate, like hydrogen carbonate, that is KHCO3. That's the total mass. That's the total mass when it is decomposed. So we got K2CO3 and then carbon dioxide and then water. So after getting the mass of KHCO3, I have to find out the mass of K2CO3. I'm going to subtract the total mass from KHCO3. So then I would be getting the mass of K2CO3. I would be getting the mass of K2CO3. This is the remaining solid that is present in your crucible, that is K2CO3. I have to find out the percentage by mass of K2CO3. So mass of K2CO3, I got 1.99 divided by the total mass, that is 12.00 multiplied by 100. So that would be your percentage yield. That would be your percentage yield, and that's it. Simple is that I was telling you initially. First of all, you have to find out the mass of K2CO3, because to find out the percentage by mass of K2CO3, we must have the mass of K2CO3 divided by the total mass multiplied by 100. So this all calculation is just due to find out the mass of K2CO3. Once I got the mass of K2CO3, so I will be finding the percentage by mass of K2CO3. Okay, now suggest why using a mass of 1.20 gram of mixture would mixture in a less reliable answer. That's the very conceptual question, you know. Basically the thing is, we know the formula for percentage uncertainty. Percentage uncertainty is equal to the uncertainty of balance, that is 0.01 divided by 1.20 multiplied by 100. So the percentage uncertainty is going to be 0.08%. If I'm going to take this much mass, when they have given in the question that was 12.00 grams. Let me calculate the percentage uncertainty by this one. So it's going to be no, no. This is going to be 0.83%, and this is going to be 0.08%, right? Okay. So you can see when I'm taking this much mass, so I'm getting 0.83 percentage uncertainty, 0.83% uncertainty, you know. And when I'm going to take 12.00. When I'm going to take 12.00, so I'm getting 0.08 percentage uncertainty. So I can say the smaller mass, the smaller mass, the smaller mass increases the percentage uncertainty. So making the result less accurate. So I have to write it down, right? So let me, yeah. So I can say using a smaller mass will increase percentage uncertainty. Percentage uncertainty, and it would make the result less accurate. Got it right? Question 5, they are saying, okay, the halogenoalkane of 2-chloro-2-methylpropane may be prepared from 2-methylpropane, 2-all like alcohol to halogenoalkane. That's a nucleophilic substitution. 1, 2, 3, 4, 5, 6, 7. Okay, 8, 9. Oh my God, 8, 9, 10. Name the type and mechanism of this reaction. Of course, it's a nucleophilic substitution. It's a nucleophilic substitution. Add to the diagram the dipole relevant to the mechanism. Okay, since oxygen is highly electronegative, it's going to be partial negative. Makes this hydrogen and this carbon partial positive. You know why? Oxygen is going to pull electron towards itself. Oxygen is going to pull electron towards itself, making the two atoms partial positive. That becomes polar. Step 2 should be carried out in a fuming cupboard. Give a reason why this precaution is necessary. Let me see step 2. In a fume cupboard, 20 cm cube. Okay, hydrochloric acid is toxic. That's why we are going to use fuming cupboard. Okay. Explain why it is necessary to open the tap of the separating funnel after each inversion in step 2. What we are doing, in fume cupboard this much hydrochloric acid to the separating funnel in a portion of 3 centimeter cube. After each addition, stopper the funnel and invert it several times. Open and close the tap after each inversion. Why we are opening and closing the tap? In this reaction, gases are formed. To release the pressure of a gas inside the funnel, so the tap should be opened. Otherwise the pressure would build up, it can explode. Or the diagram shows the separating funnel in step 5. State with a reason which layer, X or Y, is the aqueous layer. Since we know that water has a higher density, they have given the density of the organic substance. That's going to be 0.78 and 0.87. That's lower than 1. That's less than 1. We all know that the density of water is 1. More denser, so it would be the bottom layer. Layer Y is the aqueous layer, as the density of water is 1, and upper layer is of 2-chloro-2-methylpropane, which has a density that is this. Simple. It's a simple and easy concept. Or give the reason why NaHCO3 was added to the separating funnel in step 5. So what's going on in step 5? I can see that in step 5, add NaHCO3 solution in 2 cm cube portions of the to the separating funnel. Shake the funnel after each addition, invert and open the tap. Continue until no more bubbles of CO2 are seen. The thing is, I have added HCl. HCl is an acid. I'm adding hydrogen carbonate. That's a base. That's a base. So give a reason why NaHCO3 was added: to neutralize unreacted HCl. To neutralize unreacted HCl. To neutralize unreacted HCl. right? To neutralize unreacted HCl. That's it. So give the reason why anhydrous sodium sulfate was added in step 6. Sodium sulfate, you can see in step 6, allow the layers to separate in a funnel. Again, dispose of the aqueous layer, run off the organic layer into a clean conical flask and then add anhydrous sodium sulfate, stopper the flask, shake the contents and allow this to stand until the liquid becomes clear. So this substance is used to remove water, dehydration. So I told that this is to remove water. And okay, identify the three errors in each case describing the problem that would occur due to this error. Number one, water in should be at the bottom. Water out should be at the top. That's the first thing. The position of the thermometer should be just in front of this condenser so that I can measure the temperature in an accurate manner. And it should be open because the pressure would build up, right? So number one, position of the thermometer is too high. There would be inaccurate measurement of the temperature. Water in and water out of the condenser is wrong way around, as water in should be at the bottom, right? Uh, because when water in at the top, so the water would just wash away. It would just leave the condenser, so there would be insufficient cooling. And if the condenser is not sufficient cool, so the condensation would not occur. What's the job of condenser? What's the job of condenser? Just to convert the gas into liquid. Error 3, there is no outlet. There is no outlet of the condenser, so the pressure would build up. Generally, this is the condenser. If you remember, generally we set up these things so that the liquid will be entering into this conical flask. So there is a, like, you can say, gap between the condenser and a conical flask. Okay. Or describe a significant difference between these spectra and how this difference could be used to monitor the progress of the reaction. So you can see, describe a significant difference between these spectra. It's 2-methyl propane 2-ol and it's 2-chloro 2-methyl propane, right? So infrared spectrum of 2-methyl propane 2-ol, that is this, has a peak at this one, which is not present in 2-chloro 2-methyl propane. As the reaction progresses, OH substituted by Cl, so peak disappear. Like simply, in this spectrum, I can see the peak of alcohol, but in this spectrum, I can't see the peak of alcohol. Why? Because it's a nucleophilic substitution reaction. So the chlorine is going to substitute alcohol. That's it. Now they are asking to calculate the percentage yield. A student started with 10 cm cube of 2-methyl propane 2-ol. They synthesized and collected 5.60 gram of pure 2-chloro 2-methyl propane. Percentage yield. Again, the same question. First of all, I have to calculate the mass of 2-methyl propane 2-ol. So they have given the density. Density multiplied by volume is the mass. Density is 0.78 gram per centimeter cube, and the volume of 2-methyl propane 2-ol is 10 centimeter cube. Okay, so I got the mass. Then the mole of mass over mr, I got the mole. The mole ratio is the same. The mole ratio is the same as the ratio is 1:1. It would be the mole of 2-chloro 2-methyl propane as well. Then I have to calculate the mass. Again, mass is equal to Mr. moles. The MR of 2-chloro 2-methyl propane is 92.5. I would be getting the mass of 2-chloro 2-methyl propane. As I told you, the same concept. I have to find out the percentage yield. Mass, okay, divided by 9.75043 multiplied by 100 would give you the percentage yield. Okay. The mass that they have given in the question is 5.60. The one that I found is 9.75. I'm going to divide these two masses multiplied by 100. I would be getting the percentage yield. That's it. In the previous question, it was percentage by mass. This is percentage yield. There is a difference. There is a difference between the percentage yield and the percentage by mass, right? So that's an easy paper. I'm going to just upload it. You can see, and inshallah, it would help you a lot. Okay. Thank you.